This is problem 1357. It's a pretty simple problem, but I wanted to talk to you about it just to make sure everyone has seen this and we understand what this figure is all about. Because this is something that comes up a lot and it helps us understand what some of the topics that we talk about in chapter 13 are really all about. So this figure presents itself in the book by drawing this diagram. It's essentially an XY plot, although it's non-quantitative, and our y-axis, or semi-quantitative maybe we'll say, our y-axis is energy, and our x-axis is progress of reaction from start to finish. The start of the reaction is always shown over here on the left, okay, and the end or the finish of the reaction shown over on the right, okay, so it's kind of a measure of this progress of the reaction as things are converted from starting materials into products. This diagram is oftentimes referred to as a reaction coordinate diagram, or just a reaction coordinate. And it's meant to basically model the progress of reactants turning into products, okay? So you're asked to label several different things on this type of diagram, and I wanted to harp on that and teach you a little bit about what that is, okay? So first off, this line right here is sort of the starting point of our diagram, and that corresponds to the reactants. It's always going to be the reactants here at this line, okay? Likewise, over here, there's always a flat line. That corresponds to the reaction products. Sometimes the products line is below the reactants line. In this particular case, that's what we see. So the distance, or the gap between the two lines, is our enthalpy of reaction. The heat of reaction. Okay. Now in this diagram, the product sign is lower than where the reactants were, okay? So basically what that means is that we're going to have a net exothermic reaction. This reaction is going to give off heat energy, okay? We could have drawn, if we wanted to, this line up here somewhere in this range, and if this line is above where we start, that would be indicative of an endothermic reaction where heat energy is going to be absorbed from the surrounding. But regardless, whatever that change is between the starting place and the end point is the enthalpy of the reaction. Okay. Now there's one more important topic to label on this diagram. Okay, and this is going to be our EA, our activation energy. Notice this region between the two. There is drawn in this energy hump. Okay, this energy hump. That is very important because the magnitude of that hump is E sub A, or our activation energy. Okay, that's our activation energy, given the abbreviation EA. It's from our starting materials right to the top of our hump here, okay? That top of the hump is referred to as the transition state. It is oftentimes sort of a hypothetical, I hesitate to call it imaginary, but a hypothetical substance that exists somewhere between the reactants and the products, okay? Generally speaking, we cannot really isolate that material very often, and it doesn't necessarily exist as a stable compound, but it's sort of an imaginary thing, or a transitioning between our two materials, between our reactants and our products, okay? Now, the thing is, for this kinetics chapter, the extent of that activation energy, the magnitude of it, is very, very important for determining how fast reactants can be converted to products, for determining the overall rates of reaction. It's an extremely important parameter governing the kinetics, because to get to the products, we have to get over that energy hump. So it turns out that the magnitude of this EA term is extremely important for determining the rate. It's one of the most important factors, okay? And the reason why is because for reactants to get to products, that reactant molecule has to overcome that hump. It has to have sufficient energy to overcome that hump, and if it can't, it stays as a reactant, okay? This is why increasing the temperature of our reaction mixes generally increases the rate of reaction. The reason why is because if we increase the temperature, a larger fraction of our reactant molecules will have sufficient energy to get to this point. And once they get over that point, they can go ahead and form products. A fraction of the molecules actually might come back to the left, okay, and actually reform the reactants. But they have to get here. They have to overcome the activation energy if they're going to form products. So for measuring the rate of formation of this, the extent to which that can occur is absolutely crucial. And that's why that term is going to appear in that Arrhenius equation that's going to govern our rate constant K. More on that later, but I want to walk through this problem with you just to make sure everyone understands the extreme importance of activation energy on rate constants.